Plate tectonics. My name is Austin Rosypal, and today we're going to learn what they are and how we know they exist. Would you be surprised if I told you that North America is essentially a massive island that is moving extremely slowly? Would you be surprised to learn that all the continents are moving relative to each other? What causes this motion, and what are the consequences of it? The answer lies in titanic subterranean slabs of rocks called tectonic plates. The theory of plate tectonics accounts for volcanic activity, the formation of mountain ranges, and the cause of earthquakes. We'll get to these specifics later, but first, let's talk about what plate tectonics even are. The idea of plate tectonics originated with the scientist Alfred Wegener, a German geologist. He proposed a theory of continental drift, hypothesizing that the continents of today are actually all remnants of a past megacontinent, which he dubbed Pangaea. Wegener observed that rocks along coastlines of different continents matched and aligned like pieces of a jigsaw puzzle. This was also the case with fossil records. Fossils belonging to same species, 300 to 210 million years old, were found along coastlines of distinct continents with very different modern climates, implying a past land bridge or continental unification, the latter being much more probable. A few years later, a field of study called paleomagnetism vindicated the late Wegener's ideas of continental drift by using magnetic moments in layers of rock to show that continents indeed move with respect to the magnetic poles and relative to each other. These observations indicate that a mechanism must have enabled the continent to separate into the modern constituents. But how could they move? In the 1950s, a geologist at Princeton University named Harry Hess established the theory that new Earth crust is produced at mid-ocean ridges in a process called seafloor spreading. Hess combined evidence that sediment layers are thinner at mid-ocean ridges and earthquakes predominantly happen along mid-ocean ridges to support his theory. But this also implied that new sheets of crust were forming and moving away from the ridges. These sheets of crust that are created at mid-ocean ridges eventually encounter continental crust and sink beneath it, returning back to the interior of the Earth. GPS tells us that these plates are moving about 1 to 15 centimeters per year, hence taking the plates millions of years to recycle. One of the most notable aspects of plate tectonics is the effect of earthquakes. Earthquakes occur when plates grind against each other or break in the subduction process, typically around mid-ocean ridges and faults, creating distinct patterns of earthquake activity, as can be seen in this map diagram. The red lines indicate the tectonic plate boundaries, and the orange circles are earthquakes that have occurred in the recorded past. As we mentioned earlier, volcanoes and volcanic activity are another major source of evidence supporting tectonic plate theory. Volcanoes are formed when the movement of adjacent plates facilitates the rising of magma from Earth's interior up through cracks in the surface, emitting lava and forming the stereotypical volcanic cone shape over time. In conclusion, remember that the map of today looks a lot different than the map of millions of years ago, and will also look different in the future. This is because the continents and ocean floors are moving thanks to plate tectonics.